In a previous lecture, we have seen matte smelting, and I have illustrated matte smelting by solving 2 problems or rather 3 problems. Now, I thought that let me give you 2 more problems and discuss the solution of these problems, so that you can understand the quantification of matte smelting. Now, here is the next problem, that is in continuation with my previous lecture, that is the problem number 4th. The approximate analysis of copper concentrate is as follows: Cu2s, Fe(S2), SiO2 and all are given. The concentrate is smelted in a furnace in presence of iron ore and limestone. Now, both are here used as a fluxing agent. The analysis of iron ore is given and that of limestone is also given. The grade of matte is 45% and the ratio of SiO2 is to FeO is to CaO in slag is 45 is to 40 is to 15. The ratio is also given. The slag is forming in this particular ratio of the different components of the oxides. The oil amounts to 12% of the charge and analyzes the composition is also given to you. Now, in say most of the matte smelting operations, very often it is required to use extra source of energy, and sometimes it requires, it depends on the process, it depends on the say analysis of the ore and sulfur content and so on and so forth. So, it is quite possible that some of the matte smelting operation they do require extra amount of fuel. So, here 12% of the charge, that is the fuel which is used and composition is given, air is 10% excess. You must have noticed by now in various lectures, say on roasting or the smelting and so on, the chemical reactions accompanying the transformation of one phase to another in roasting as well as in smelting, it does not occur with the stoichiometric amount of air. You always require some amount of excess air, and so what should I say at this particular point, that the industrial operations they always require an excess amount of air. Now, it is up to the skill of the operator how beautifully you control the excess amount of air. Somebody may do at 10%, somebody may do 20%, somebody even do with 30%. So, all that is required to the control of excess air, because the control of excess air, it is also important, the more air you use, the more nitrogen will enter and more nitrogen will take the heat from the reactor to the atmosphere. So, that is also an important issue over here. Now, you calculate per ton of concentrate, weight of each flux and volume of air and so on. Now, the next problem is, say copper ore contains 16% copper, 30% iron and so on. The smelting of this ore produces a matte whose grade is given, the flux is limestone and slag contains 14% CaO. Now, various data on the heat are given. You can go through these data and understand those data, because whenever there is a formation of slag, it is also accompanied by heat of formation. I mean, you do require to supply extra amount of heat for heat of formation, and here also given at what temperature they leave. So, you must have understood from the statement of the problem that I would like you to do heat balance also, and that is what is written. You have to calculate calcium carbonate, total heat supplied and total heat leaving the furnace. So, these are the 2 problems. Now, the answers are for all the problems, say in the previous lecture problem and this one, they are given over here. So, I will proceed now to discuss the problem. I hope by now you must have read the problem and you must have understood how to solve these particular problems. So, let us discuss the solution of these problems. So, fourth, let us consider say x kg iron ore, x kg iron ore, y kg limestone, and z kg slag. Now, let us first of all do SiO2 balance, because the components in the slag and their proportions are given. So, I will make use of this. So, now if I do SiO2 balance, So, SiO2 balance will lead me 0.19 x plus 0.07 y plus 260, that is equal to 0.45 z. That is, you have to take into account SiO2 from all sources. Now, let us do CaO balance. Let me put this equation as number 1. To CaO balance, then I get 0.52 y, that is equal to 0.15 z, that is equal to 0.15 z. Let us put this equation number 2. Now, in order to get, because we have 3 variables, I need one more equation. So, I am looking for an iron balance. Now, before I do iron balance, I have to see the various sources from where iron enters and it leaves. So, first of all, I have to find a grade of MET is given, that is 0.45, that is equal to 160 upon 200 plus MFES. So, if I solve, I get from here MFES, that is equal to 155.6 kg. Now, I know that much amount of iron is going into the MET. Now, I can do the iron balance and find out the amount of iron that is entering into the slag. Now, I have to do iron balance. Now, I have to do iron balance. So, if I do iron balance, I write iron in concentrate, iron in concentrate. I have to see iron from all sources plus iron in iron ore, iron in iron ore, that is equal to iron in MET, iron in MET plus iron in slag. So, if I write down all the values from where the iron is entering, and if you do that, then I will be getting an equation which is 0.57 x minus 0.31 z, that is equal to minus 129.7. So, now I am summarizing all the 3 equations, that is 0.19 x plus 0.07 y minus 0.45 z, that is equal to minus 260. So, next is 0.52 y minus 0.15 z, that is equal to 0, and 0.57 x minus 0.31 z, that is equal to minus 129.7. So, this is equation 1, this is equation 2, this is equation 3, 3 variable, 3 equation one can solve. So, the value of x 133.6 kg, value of y 191.5 kg, and value of z, that is equal to 664.0 kg. So, that is the answer about the what is asked. So, x is in fact iron ore. This is limestone and this is slag. Now, let us calculate about the volume of air. Volume of air. First of all, we have to find out the amount of oil. So, amount of oil is 12% of the charge. So, now the charge, you note that charge consists of whatever you are charging to convert the charge into MET. So, you are charging concentrate, iron ore plus limestone, not only concentrate. So, it is 12% of all. So, the charge total is 1325 kg. You have to add up all the amount. So, the oil amount of oil that is equal to 159 kg, and accordingly the carbon that is equal to 135 kg, and hydrogen that is equal to 24 kg as per the percentages are given. So, I am writing here 11.3 kg mole and hydrogen is 12 kg mole. So, once I know this thing, so I can calculate now theoretical oxygen, theoretical O2 required for combustion, that will be equal to 17.3 kg mole, right. So, we are considering now for complete combustion, and that is important. Nothing is given, you can only calculate by considering complete combustion, that is C plus O2 CO2 and H2 plus half O2 is equal to H2O. So, now you also require air to oxidize say iron to FeO and sulfur to SO2. So, we have to find out how much amount of oxygen would be required here. So, for that we have to do something. So, first of all we will do sulfur in mat, because we have to find out how much amount of sulfur is going to the gases. So, sulfur in mat, that is equal to 3.018 kg mole. You know, sulfur in mat consists of Cu2s and Fe(s), and you have to convert it and you have to get sulfur in mat. So, now sulfur in charge, say sulfur in charge that will be equal to 9.417 kg mole. You have to see the sulfur which is entering into the furnace from the different sources, you do that and you will get this value. So, sulfur to gases, sulfur oxidized to gases, you can very well guess now what will be, that will be 9.417 minus 3.018, and that will be equal to 6.399 kg mole. Now, immediately I can calculate the oxygen required, O2 required. I hope you must be remembering the reaction will be S plus O2, that is equal to SO2, because the problem does not say SO3 or anything. So, you have to consider formation of SO2. So, oxygen required, that will be equal to 6.399 kg moles. Now, about the iron oxidized, we can calculate the amount of FeO, and from the FeO we can calculate how much oxygen is required by Fe plus O2, that is equal to half O2, that is iron oxidized. You can calculate, that will be equal to 664 into 0.4 upon 72, that is equal to 3.689 kg moles. So, oxygen required, that will be half of it, 1.844 kg mole. So, now also the problem says there is some oxygen is also available from charge, you know, you are charging Fe2O3. So, oxygen available and available oxygen is only from Fe2O3. You know the amount of Fe2O3 because they calculated its amount, and that oxygen will be 1.015 kg mole. Now, theoretical oxygen required, that is theoretical oxygen required, let me put derived from air, which is derived from air, because you have to subtract what Fe2O3 is supplying. So, that will be whatever oxygen required for combustion plus oxidation minus oxygen available. Oxidation Fe to FeO as we have calculated earlier, and sulfur to SO2. So, if I do all, then theoretical oxygen required would be 24.528 kg moles. Now, once I know the theoretical oxygen required, then there is no problem, 10% excess. So, actual oxygen will be 1.1 times this, and I can calculate the amount of air. So, the amount of air actually required, that will be equal to 2877.95. So, that is the answer. This is the meter cube. All that you have to divide theoretical oxygen by 0.21 and multiply by 22.4 and take 10% excess of that. So, you will get this amount of air. Now, the next is the gases which are forming. So, gases which are forming SO2, you have CO2, you have H2O, you have nitrogen. Now, mind you, since we are using excess air, so there will be oxygen also in the flue gases. So, I will put here, that is SO2 is 6.399, 11.30, H2O 6.00, nitrogen 101.448. Note the very large amount of nitrogen that is obtained in the flue gas, because nitrogen is inert, and whatever you supply, it will go out with the flue gas. And not only this, it will also carry a large amount of heat, and oxygen is 2.4528. Now, these values are all in kg moles. So, I can write down the percentage. So, percent will be in percent 5.01, 8.86, 4.70. Nitrogen, note its amount is very high, therefore, one has to be very cautious in using the excess amount of air, because it does not matter if you have a large amount of heat that is more than required, then there is no problem, but whenever there is a heat deficit, then this control of excess air is important, one. And second, the nitrogen will also carry a large amount of heat. The quality of heat will be very high, because the temperature of the flue gases is very high, at least the temperature will be that of the smelter, 1000 or 1100 degree Celsius. So, higher is the temperature, higher is the quality of heat. So, when the quality of heat is very high, then it takes a very large amount of heat with it, and appropriate waste heat recovery devices must also be thought of to recover the heat. So, that is what the important. Oxygen is 1.93%. So, the total flue gas, that is equal to 127.5998, that is in kg moles. Of course, this becomes 100, it should become 100. So, the volume of the gases will be 2858.235 meter cube at 1 atmosphere and 273 Kelvin. Now, again you are noting here the ratio between volume of air and volume of flue gas is approximately 1:1. So, that is all, that also says that the solution to your problem is rather okay. Now, let us take it problem number 5. Problem number 5 says, say you are charging I am putting in kg, the charge is say copper is 160 kg, iron 300 kg, sulfur 320 kg and SiO2 that is equal to 220 kg. Say basis of calculation is 1000 kg concentrate. Based on that I converted this amount. So, you get here MET, and MET contains Cu2s as per the statement of the problem and contains FES, it contains slag, that contains FeO, SiO2 and calcium oxide. Then you have gases, you have SO2 and N2. Now, here you have to do heat balance also. So, as I have said that before you enter into the venture of heat balance or into the doing of heat balance, you must be very clear about the material balance, and all the values should be okay for heat balance, because otherwise the mistake will be carried over till the end of the heat balance. So, be careful while doing the heat balance, material balance first. So, it is given MET grade is given, MET grade is given, that is 50%, and it is also said that the slag it contains 14% CaO, which is formed by the addition of limestone. Now, we have to calculate all their amounts. So, if I calculate now, you know the definition of MET grade, that amount of copper upon amount of MET. So, if I do that, then I will be getting amount of Cu2s and amount of FeS. So, Cu2s will be 200 kg and FeS will be 120 kg. This is how we know now the amount of MET. Now, we have to calculate the amount of slag. Now, since 14% CaO is in the slag, so that means, and we also know now here little bit chemistry of MET smelting is also known to you. In this particular problem, the slag will contain FeO, SiO2 and CO, and that is all. There is no other source of any other component in the slag except the 3 which I mentioned. What are they? FeO, CaO and SiO2. We are given 14% CaO. So, balance is FeO and SiO2. So, that means the slag will have 86% FeO plus SiO2. Now, we know say SiO2 that is equal to 220 kg, because whatever SiO2 in the charge it enters into the slag, that is what the chemistry of MET smelting says. And FeO, now you have to find out FeO in slag. So, FeO in slag that will be equal to iron in ore minus iron in MET. That iron will go into slag. If I want to find out FeO, that will be into 72 upon 56. So, that will be equal to 287.5 kg is the amount of FeO that is entering into the slag. Now, let x kg is the weight of slag. Now, then x I can easily find out, that will be equal to 220 plus 287.5 divide by 0.86. So, I get now x that is equal to 590.1 kg, that is the amount of slag. Now, the whole idea of knowing the amount of slag is to determine now SiO2, FeO and calcium oxide. So, now about the gases. So, we have to know the amount of gases. Now, for the gases we have to do sulfur balance. We have to do sulfur balance. Now, what this sulfur balance says? Say sulfur in charge that is equal to sulfur in mat plus sulfur in gases. That is what is sulfur balance. So, well, I am doing sulfur balance in kg moles. However, you can do in kg also, as long as you are consistent with the units and with all, there is no problem at all. So, sulfur, I will write down a sulfur in charge, that is 320 upon 32, sulfur in mat, that is 200 upon 160 plus 120 upon 88 plus sulfur in gases. Now, by simple mathematics I can find out, say sulfur in gases, that will be equal to 7.39 kg moles. So, therefore, SO2 would be, SO2 would also be equal to 7.39 kg moles, because you know S plus O2 that is equal to SO2. Now, say O2 required for this, O2 required, that will also be equal to 7.39 kg moles. Now, the weight of calcium carbonate, since we know amount of slag, we know percentage calcium oxide, from there we can find out the weight of calcium carbonate, that will be 147.5 kg. Easily you can find out, say calcium oxide is 14%, weight of slag is 590.1 kg. So, 14% of that 590.1 is the calcium oxide, and from there you convert to kg mole and find out the calcium carbonate and so on. So, that is how the weight of calcium carbonate. Now, weight of calcium carbonate is known to you. So, we know now moles of CO2, because calcium carbonate on dissociation it gives to you calcium oxide plus CO2, and this CO2 will be in the exit gases. So, moles of CO2 that will be equal to 1.475 kg moles. Now, slag contains FeO also. So, oxidation of iron will also require oxygen, and that we have to find out. So, O2 for oxidation of iron that you can calculate, it will come 1.996 kg mole. So, total oxygen required, total O2 required, that will be equal to 9.386 kg mole. That is, you have to add one for sulfur to SO2 and iron to FeO. This is where you require the oxygen. So, accordingly nitrogen would be 35.29 kg moles. So, I can calculate now the amount of gases, that will be say SO2 7.39, CO2 1.475, that is kg moles, also kg moles, and nitrogen, that is equal to 35.29 kg moles. Now, with this we have done the so called material balance. Now, we are ready to perform heat balance as asked in the problem. So, now, let us do the heat balance. Let us perform now the heat balance. Now, remember, in heat balance the basis of calculation is always 298 Kelvin, unless otherwise specified. I mean 298 Kelvin, I mean because the heat content and Cp values, they are all given at 298, heat of formation of compound and so on, they are all available at 298 Kelvin. So, it is customary, or it is rather it is desired that you choose the reference of calculation is 298 Kelvin. However, you can choose any temperature, but then you have to convert the available value into that temperature. So, that is what I thought I will tell you. So, heat balance, what heat balance is, I will again make a diagram, so that I write down all the values over here, what I have here. So, I have here copper ore, and copper ore is charged at 298 Kelvin. Then we charge limestone, that is also charged at 298 Kelvin. Then charge air, air is also charged at 298 Kelvin. Now, we have met, I mean met means MATTE, Cu2s FeS. So, met, we have Cu2s, that is equal to 200 kg, FeS, that is equal to 120 kg, and its temperature is 1400 Kelvin, that is important. Then the slag amount we have to write down, FeO, we have SiO2, and we have calcium oxide. So, FeO is 287.5, I mean they are all in kg, SiO2 220.0 kg, and it is 82.6 kg, and it is being discharged at 1400 Kelvin. Next, we take the gases. We have SO2, we have CO2, we have nitrogen. SO2 7.39, 1.475 and 35.29, and the gases are discharged at 500 Kelvin. So, this is what the material balance output I have written here, so that now I can do heat balance effectively. So, let me give other thermodynamic values as required for the calculation. It is also given heat content in MET, heat content of MET at its melting point, and melting point is, let us take 1273 Kelvin, that is equal to 205 kilocalorie. Remember, it is per kg, not kg mole, and specific heat of liquid MET, specific heat of liquid MET is also given 0.14 kilocalorie per kg, remember, degree Celsius. So, that is also given. Now, some values on the heat content is also given. So, H 600 minus H 298 N2, that is equal to 2126 H600 minus H298 oxygen 2210, that are given in kilocalorie per kg mole. Now, here onwards what value I am giving, they are all in kilocalorie per kg mole. Now, H500 minus H298 for SO2, for N2 and for CO2. So, that is equal to 2108, nitrogen is 1418 and CO2 is 1987, values are in kilocalorie per kg mole. Similarly, the H 1400 minus H298 SiO2, CaO and FeO. This is also you can write down here H14400 minus H298, and similarly you can put it here. So, this value is 17370, 13430 and 14520, that are again all in kilocalorie per kg mole. Now, it is also given heat of formation of slag, heat of formation of slag, that is also given 140 kilocalorie per kg of slag. Now, some heat of formation values are also given, say delta H naught FeO, naught means 298, delta H naught FeO, that is minus 64,300, that is kilocalorie per kg mole. Then delta H naught FES minus 23,100 kilocalorie per kg mole, delta H naught SO2 minus 70,940 kilocalorie per kg mole, then delta H naught calcium oxide, that is equal to minus 151,600 kilocalorie per kg mole, then delta H naught CO2, that is equal to minus 94,450 kilocalorie per kg mole, and delta H naught calcium carbonate, when it is formed from its element, that is minus 289,500 kilocalorie per kg mole. Now, I think all these data are given to you. Now, one can now find out the various terms concerning the heat input and heat output. Since the reactants are supplied at 298 Kelvin, so no sensible heat will be entering into the reactor because they are at 298 Kelvin. Now, the heat supply term first will be sulfur oxidation and second is iron oxidation. That will constitute the heat input term. So, sulfur oxidation you know, that is 7.39 into 70,940. Now, let me put here, they are the heat liberated. Heat liberated. Now, because I am not putting here minus sign, that means I know that they are exothermic reaction, that is why I put the term heat liberated. For iron oxidation to FeO, that will be 3.993 into 64,300. So, if you sum total, then the heat liberated that will be equal to 781,000 kilocalorie. Now, why have you used heat liberated? Because the decomposition of limestone is an endothermic reaction. So, heat of decomposition heat of decomposition of calcium carbonate, that is equal to 64088 kilocalorie. Mind you, this is a highly endothermic reaction and you see that that much amount of heat will be absorbed. Now, I had already given the thermochemical data in order to calculate the heat output. Now, using those thermochemical data which has been given to you in the problem, heat output by various outputs can be easily calculated. So, I will make now the calculation for you. So, heat input first of all, heat input, that is consists of say oxidation reaction, and the amount of heat input can be easily calculated by using the heat of formation data, and that is equal to 781,000 kilocalorie. Heat absorbed, that is equal to 64088 kilocalorie. So, therefore, heat available that would be, we have to subtract it, and that is heat absorbed. So, just for the convention I put this as a minus and this is exothermic reaction, so I will put it plus, so that no confusion is there. So, heat available would be 716,912 kilocalories. Now, we can write down the heat output. Now, heat output consists of several items, for example, FeO, CaO, heat of formation and so on so forth. So, I will write down all the things for you. For sensible heat in FeO, sensible heat in FeO, of course, I will put here in kilocalorie, that is equal to 57979 kilocalorie. Sensible heat in CaO, sensible heat in CaO, that is 19809. Heat of formation of slag, heat of formation of slag, that is 82614 kilocalorie. Now, sensible heat in SiO2, sensible heat in SiO2, that is equal to 63690. Now, all these four, it correspond to heat taken out by slag. Then, sensible heat in matte, sensible heat in matte, that is equal to 71290 kilocalorie. Sensible heat in gases, sensible heat in gases, and you know the gases comprise of SO2, CO2 and nitrogen, that is equal to 68850. Then heat loss, as said in the beginning. Now, if not mentioned, it is in solving the problem, normally people take 10% of the heat available, if not given. If it is given, then you have to take the actual. So, heat loss, let us say 10% of available heat. of available heat. So, this makes 71691 kilocalorie. So, total heat output, that is 435623, and you see that heat input is much greater than heat output. So, the process is autogeneous in nature.